All right, so now what I'm going to do single slit diffraction. So I'm going to shine the laser through a single slit. Sorry. Okay, so, come on. So there you see it, right? So you see when light passes through a single slit, you see that incredible bright central spot, and then you see the interference pattern. You can see that the intensity dies off. All right. Okay, so that's what we're going to talk about. So there, how's that? Right? So that's single slit diffraction, the super bright central region, and then you see a pattern, and the intensity dies off really quickly. Okay, remember I talked about Huygens? He was one of the scientists that disagreed with Newton, which took a lot of courage, right? And he said that light was made out of waves. So there's something called the Huygens principle. Huygens principle. So here's the single slit, right? Magnified big time. So Huygens principle says that every point in the tiny, tiny slit is a separate point source of a spherical wave, right? So think about it. Every single point, in this tiny little slit, you can think of as a source of a spherical wave. Now, these waves, they're going to be really small, right? And so he had a funny term. He called it a wavelet. All right? So here. So basically, this is the single slit. So, how many points are between a single slit? An infinite number, right? And so what he said, every one of those points is a source of a spherical wavelet. Okay? That's kind of funny. And then, he just used the interference for all of those wavelets. Okay? So, when we were doing this, we just always assumed there was one source, right? That's split into two sources. But what Huygens is saying, no, he's saying, for even a single slit, you have an infinite number of sources of light. Oh my goodness gracious, right? So that's incredible. All right, now, you can imagine the mathematics is horrendous, right, when you're dealing with something like that. So we're going to just skip it, sorry, and we're just going to give you the results. Okay, so this is for a single slit. All right, so here's the first result. The destructive interference occurs when A sine of theta equals P lambda. Now, why they use P, not M? I don't know. Who cares, right? So now the index is P, okay? So again, this tells us where the destructive, the mins, occur, all right? Okay, that's cool. And then the second result is between the mins, you get a max. Well, that sort of seems reasonable, right? And of course, the central max, this thing, occurs at P equals 0. P equals 0. Oh, that's nice. All right, so this is a math question, really. When light passes through a single slit, dark bands appear on a viewing screen at angles given by A sine theta equals P lambda. I just told you that, where P is 1, 2, 3, and so forth. For the dark bands to exist, what must be the relation between lambda and A? Again, this is just totally math, or trig, I guess. So pause your video and figure it out. Okay, we're back. That's the answer, right? Because, sine, okay, solve for sine. Sine is P lambda over A. Well, sine is less than or equal to 1, right? You can't have, right? Sine goes between 1 and negative 1. So, P is 1, 2, 3, 4. So that means that lambda has to be less than A for this thing to be less than or equal to 1. That's all. Not a big deal. So lambda has to be less than A, which is pretty simple, right? Because the wavelength of light is so incredibly small. Okay, what happens when lambda equals A? So pause your video and figure it out. Okay, we're back. if lambda equals A and P equals 1, then what's theta? 90 degrees. So you just see this big white band, all right? You just see a central white band. Okay. Now, this is what, okay, all right, so yeah. I already said that. Okay, so what I want you to do now, and again, you do it. So this is single slit diffraction. We know this equation here. We know, so figure out an equation for yp in terms of p, l, lambda, and a. And yeah, okay. And you're allowed to use the small angle approximation. So we're going to assume that we're not talking about something way down here, way up here. We're just talking about things that are close. So use small angle approximation. So tangent equals sine. And please figure it out. So pause your video. All right, we're back. Okay, so as before, y, we're going to subscript it with a p now, right? yp, I don't know, equals L tan theta. No kidding, right? I mean, right? This is L. It's not labeled, huh? Whatever. This is L. That's y. That's theta. So y equals L tan theta. But now we're going to use, but now we know that A sine theta P equals P lambda. So therefore, sine theta P equals P lambda over A. So therefore, we're going to have, this is equal to L sine theta, which is L P lambda over A, which is not cool. Better to write it like this. Because P is an index, right? P is an index. P is 1, 2, 3, so forth. There you go. All right. And again, this is only good for, close, when you have small angles. We cannot use this equation when we're way down here because then the small angle approximation just doesn't work. All right? Okay, we want to talk about the width we want to talk about this width, and you'll see why. We want to talk about that width. Okay, you can tell that the width is symmetric about this line, agree? So this here is the same as that there. So there's symmetry, okay? So therefore, using this equation that we just figured out, this equation here, what is the width? What is this W? What's the width? Well, it's sort of obvious, right? It's just yp times, y1, right? It's just this y1 times 2. So that's kind of cool. So the width is just 2y1. And use this equation. It's just 2 times 1 L lambda over A. We're going to use that. That's why I'm making a big deal about it. Now, what happens to this width? What happens to this width as this A, gets smaller and smaller and smaller? Well, what do you guess? It's going to increase, right? We already saw that. Well, look at the equation. If A gets smaller and smaller and smaller, this gets bigger and bigger and bigger. So that just agrees with what we said, but it's always a nice idea just to check things like that, right? Okay, so once again, we're not surprised. Okay, that. Yeah. Okay. All right, and so this is not a shock to us, right? When this gets smaller and smaller and smaller, the width gets wider and wider and wider. All right, wonderful. Now, look at this. So you got to be careful. So here we want lambda over A to increase. Okay? So that means there's going to be more and more spreading, right? Because the diffraction is proportional to lambda over A. So when lambda over A is kind of small, you know, there's a kind of a narrow central peak, right? When lambda over A gets larger, that central peak gets larger or wider, so it spreads out. Then when lambda over A keeps getting bigger, this is that central peak. I mean, it's really, really wide, right? It's really, really wide. Okay? So again, we see this, right? Diffraction depends on lambda over A. Well, by the way, here are the numbers. So here, A equals 10 lambda. So lambda over A is 1/10. And here, A equals 5 lambda. So lambda over A is 1/5. And here, it's A equals lambda. So, you know what I mean? Okay. All right. Now, let's go back to the double slit experiment. Okay. So this is what our prediction was, uniform intensity, and we know that's wrong because this is what it's supposed to look like. So here's the final answer. If we include our theory for the double slit experiment and we include our theory for the diffraction of a single slit, okay, so here's our double slit interference with no diffraction. Here's our single slit diffraction. If you incorporate this and this, you get this. All right, so this is double slit interference with diffraction. So notice you get a real bright primary peak, and then you get secondary peaks. They don't show very many, but they're considerably less intense than that bright peak. So basically, what I'm trying to say, is that this agrees with the data. Okay, if you include double slit with single slit, double slit interference with single slit diffraction, you actually get what it's supposed to look like. And just to remind you, that's what it's supposed to look like. Really, really bright. I mean, this has been overexposed. Really, really bright, and then the intensity just dies off. So that's exactly what you get when you incorporate the diffraction. So yay, it all works. Yay, yay, yay. All right. Whew. So that's awesome, right? So we were able to completely explain the double slit experiment, where the maxes are, where the mins are, and the values of the intensity. Everything matches. So it's a tremendous success for the wave theory of light. All right. Now what we want to do, we want to kind of change gears. So, you know, if light diffracts through a slit, like we've been talking about, don't you think it's going to diffract through a circular opening? Now, why would we care about that? Well, where do you see light going through a circular opening? Okay, biologists, where? Microscopes. Astronomers, where? Telescopes. So this is incredibly important and for biology and for astronomy. Okay? All right, so we're going to skip a whole bunch of math. Sorry. So now, instead of just, this is not a slit, it's actually a circle, right, with diameter uppercase D. It's a shame they use uppercase D because we always use uppercase D for the displacement, but such is life, okay? So now, for circular aperture diffraction, uppercase D is the diameter. Well, doesn't this look the same as the previous ones? Well, of course, it's single slit diffraction, right? It's just single slit diffraction, you know? So, of course, it's going to look to be the same. So, again, skipping all the math, sorry. The first minimum is going to happen when sine theta 1 equals 1.22 lambda over d. Now, look, this is super small angle right here for the first one. So there's another small angle approximation. You know, earlier I showed you that table that had all the angles and sine theta and theta. If you go back and look at that, you'll see that for quite well, for like up to 20, 25 degrees or so, it's also a good approximation. Okay, so this is what we had. We had tangent theta equals sine theta. That was pretty good for like 20 degrees or so. Well, you go back and look at that table. It's also a good approximation if you say sine theta equals theta. Again, theta has to be in radians, right? So this is like the second small angle approximation. We're just going to say sine theta equals theta. So instead of saying sine theta, we're just going to say theta. So theta 1 equals 1.22 lambda over d. Bingo. All right. Now, what do we care? Well, you care a lot, you know. I mean, basically, look at, if you're looking at a star, you're going to see that, right? And where do you want the star to be? You want your star to be, or a galaxy, or whatever you're looking at, you know? You want it to be in here. You don't want it to be any bigger than this, because then you're going to have all these these mins, these dark spots. So that's not going to be any good. So you really want your image to be in here, right? I mean, that's what you want, okay? So because of that, okay, so this is called the diffraction limit, okay? So this here, right? That's where you want your image. So they call that the diffraction limit. So you want everything to be inside here. And again, here's another reason why. Again, this is super overexposed. This is bright, but this is really super dim. I mean, they just overexpose it to make it easy to look at. So I mean, if you have something out here, first of all, this is going to be dark here, and this is going to be pretty dark here, so you're just not going to see it. So you want everything in here. So that angle theta 1 is the diffraction limit. Okay, diffraction limit. All right, and let's kind of talk about this a little bit. All right, this is kind of a neat little slide here. Almost got chopped off. Okay, so here's the diffraction limit, theta 1, 1.22 lambda over d. Okay, if let's say you have two stars really close, and if you see two stars really close, I mean, you want to know if they're two stars or one star, right? Let's say you're out in the middle of nowhere, and there's a car approaching you, and it's nighttime, dark, and it's really, really far away, and you just see one light, right? And then when the car approaches you, it gets closer and closer and closer, you actually see it's two headlights. So that's what I'm saying. You want to see if it's one star or two stars. Okay. If two stars, are sufficiently far apart, they can be seen as two separate diffraction spots, right? Yeah, so you know there's two stars there. You can see all the diffraction. You can see the diffraction pattern, you know? Okay, so two diffraction spots. If the sources are too close together, their diffraction spots will overlap so much that they appear as a single spot, which is right there, right? You can't say it's one spot, two stars, one star. Two sources will be resolved as two distinct sources of light if their angular separation is greater than theta 1, okay? So in other words, see here, they're both within theta 1. If they're bigger than theta 1, then you can start saying, hey, it's two sources, not just one. So that's the important thing. So here, these are just for fun. So, so in astronomy, they talk about, they have, there's degrees, right? 360 degrees in a circle. Well, there's also something called an arc second, which is 1 over 3,600 of a degree. So what's an arc second? So here's a dime. What is that? And, okay, so this is a telescope. This is the diameter of a telescope. So if you have a 5-inch telescope, 5-inch, that means the diameter of the lens or the mirror is 5 inches. With a 5-inch telescope, you should be able to see a dime 2.3 miles away or 3.7 kilometers away. Now that sounds cool, but it's nothing compared to what the astronomers do, right? Let's say we have a 2.3 meter telescope. So here, this is a star, supergiant, and it's 430 light years away. That means it takes light 430 years to travel from the star to us. That's kind of cool. Think about it. That means when you're seeing the star, you're actually seeing what it looked like 430 years ago, right? We don't even know if it's there anymore because it takes light so long to reach us. But anyway, so this star is pretty far away, right? And this is 0.055 arc seconds. So, I mean, you can really resolve things. The Keck telescopes on Mauna Kea, they have a 10-meter mirror, and there they can see 0.01 arc seconds. So basically, I mean, what's the rule? Look at that formula. So you want this theta 1 to be as small as possible, right? Because you want to be able to resolve things. So that means you want a larger and larger diameter telescope, which of course costs tons of money, right? And is difficult, engineering-wise to build. But that's why astronomers keep asking for larger and larger telescopes, because they want to be able to resolve things that are really, 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 really far away. Is that a beautiful picture? All right. Okay. All right. Now, yeah, I should say that the largest telescope now is 10.4 meters diameter. There is a 30-meter telescope planned somewhere in the world, and Europe has plans to build a 39-meter diameter telescope. So that's pretty impressive, right? Okay, yeah. Okay, let's do this. All right, please, you do it. So I want you to figure out W, the width of that central max, and use this. All right, and everything else you need. Okay, so pause your video and do it, please. Okay, let's do it. So again, y1 equals L tan theta 1, which is L sine theta 1. But we know that sine theta 1 is theta 1, whatever, 1.22 lambda over d. So we have L, we have 1.22 lambda L over d. So, all right, so that's y1, that's this. But we want the complete width, which is 2y1. So therefore, the width is 2y1, which is 2.44 lambda L over d. Ta-da! We're going to use that later, all right? We're going to use that later. Okay. Now, here's just a little history for you. It's kind of interesting. A little history for you. Oops, sorry. Okay, yeah, we'll use that. Okay, here's history. I have to read this. In 1819, there was a scientist called Fresnel. He presented to the French Academy of Sciences a wave theory of light that predicted and explained interference and diffraction effects. Almost immediately, another scientist, Poisson, pointed out a counterintuitive argument. Poisson said, according to Fresnel's wave theory, if light from a point source were to fall on a solid disk, some of the light would be diffracted around the disk and would constructively interfere at the shadow center. This prediction seemed unlikely. Okay, so just pretend, just pretend that you're Fresnel, right? This is like this big shot, science meeting, French Academy of Sciences, You've just given this big explanation about the wave theory of light, interference, diffraction, the whole thing, right? Then this other guy gets up, Poisson gets up and he says, I'm going to exaggerate. He says, you're crazy. According to what you say, if you shined light at a solid disk, it would diffract around the solid disk and make a light in the center of the shadow. And anybody with a half a brain knows that's wrong. So can you imagine how Fresnel felt at the time? Now here's the cool part. So later on, they actually did the experiment. And guess what? Ta-da! You actually see a bright spot in the shadow. That's incredible, right? I mean, there's no way you can explain that with a particle or a ray model of light, right? You shine light here, you just get a shadow. But again, the wave theory predicts the diffraction, so it predicts a bright light right there. So it's cool. Now, sorry guys, I actually have a demonstration of this. And we can't do it here. It just wouldn't. I don't want to do it here, right? Sorry, it's too much trouble. And it's just. But anyway, I usually do it in K132. It's simple to set up. You just use a laser pointer, a couple of lenses, and it's just, you know, I just have this little tiny pin, you know, like a circular pin. But it's like super small. I mean, just like a little pin, right? And I just shine a laser through it. I mean, a laser around it with some lenses to help. And then we look at it at the front whiteboard, and you see the shadow. Then you see this bright spot right in the middle. I mean, it's really cool. It looks just like that. But, sorry, I'm not going to do it here. It's just too much trouble. Sorry. If you want to see it someday, come see me. All right, that's time for a new video.